So this is ChatGPT. There's been a lot talked about it recently. You can use it to design all manner of things, even things around the house. You can get it to design a garden layout perhaps. I'm going to use it for something a little more technical, of course. And you could just give it questions in English language, and for the moment that is, and it will solve your problem. It kind of gives you different answers though each time, depending on how you ask the question. So the beauty of asking in the English language, is natural language, is that you could sort of link it into something like Alexa in the future, which means you could have something like Star Trek, where you give a command to the computer and ask it a question like, computer, what is the day today? And it'll tell you what day it is. Or you could say, computer, solve the following problem. So let's have a look. I'm going to ask it to design what should I put, design, or shall I put simulate? Or simulate, I think. Simulate a PID controller on a second order system. I'm going to make it quite simple for it. If I make it too complicated, it might have to split it up into component parts. And then I'm going to say using MATLAB. So simulate a PID controller on a second order system using MATLAB. So that might be an exercise that you do in the second year of a degree course or something. It's a simple problem to get you going. So let's see what it does. And it says, sure, here's the general outline of how you can do it. Define the transfer function. Then it's using symbolic method, and then it's telling me how it's going to simulate it. Yeah, that's the controller part. It's KP plus KI upon S plus KDS. And it's going to put feedback around it, and then that's how it's going to plot the answer. But I'll notice it hasn't actually given me the whole code. I did this before and it gave me everything, so I'm not really happy about that. So what I'm going to do is I'm going to say, give me the MATLAB code for simulation of our PID controller on a second order system, and see what that goes. Now that's a bit better. So now it's giving me everything all at once rather than splitting it up into little bits. What's the big question is it actually going to work? So what it's doing up here is it's using symbolic methods to generate a transfer function, and then this is just a classic undergraduate sort of PID controller there's no filter on derivative action. It's putting negative feedback around the system is G, the controller is C. This is the MATLAB code for negative feedback, and then it's putting a step into the system, and it's going to run it a sample interval of 0.01 of a second. Let's just type in MATLAB and see what it does. You should be able to copy that and type it straight in, see if it works. So I'm going to create a script in MATLAB. At the moment it's called untitled, and we just copy this code and just see. I mean, obviously you do need to know a little bit about MATLAB and so on, otherwise it's going to be the blind leading the blind. But here we go. So that's my code typed into MATLAB. Now I'm going to save it as something like test. Let's call it test. It's already something called test, so I'll just overwrite it, and let's run it and see what it does. Oh my goodness, there you go. Second order system. It's simulated 1 over s squared plus 2s plus 1, you can see here. and it's just given default PID parameters of 1, 1 and 1. I mean, obviously I can change that system to be anything I like. It's interesting that it's given it that way rather than the numerical way of doing it with vectors, which is the way I would have done it, but there it is. Let's speed this up a little bit, so let's increase the proportional gain to 10 and see if it might even oscillate a little bit. Let's see what happens. Run it again. Oh, there it is. You see there's a bit of overshoot now because I've put a lot of proportional action. So let's put a little bit of, I'll forget about the overshoot and let's just see if we can get rid of the offset there because it's a unit step going in. So let's put some integral action, a little bit more integral action in. Let's put 5. Not using any fancy tuning methods, of course. And there we go, we've got rid of the offset, and I can reduce the overshoot by increasing the derivative action at the expense of something else, of course. But let's just make the derivative action 3. See what that does. And there we go. That's pretty darn good, I would say. So just with you know, one line of a question, really, you can produce that. So let's try something else, which I won't be able to verify straight away, but let's ask it another question. Let's say write the code in Python, MicroPython for an ESP32 microcontroller to perform PID control. Similar sort of thing, but real time this time. See what it does. What happened? Oh, here it is. Here is a general outline of how you can implement a PID controller in MicroPython, and it's given steps. But it doesn't actually. Is it going to give me the code? Yes, it is going to give me the code. Not much point if it doesn't give me the code. While true is reading the sensor and the set point. So it's a bit like sort of pseudo code there, because of course it doesn't go into specifics as to how you're going to read that, but that's not a big problem. The error, old error is a new error plus the update. So that's just getting a previous value of the error, and the PID output is proportional times to the error plus integral time times the accumulated error. That's actually the integral. That's really the integral of the error. Should have said that's error new equals error old plus the update, which is just a straight integration. And this is a first difference, which is good actually. That you can see it just takes the error minus the previous error, which is the differential, or the first difference rather, and then control the process output and wait for while repeating the loop. It's not very, doesn't use a real-time interrupt or anything, it just goes to sleep for like 1 second. Of course you could change that. It's given these suggestions. Of course it doesn't know what the system is, so it's not going to be able to tell us you know, in any more detail what it is, but it gives us a little bit of a start. Let's see if we can do the same sort of thing in C. Write C code for a PID controller, I'll make it quite brief, on an ESP32, I'll just say micro, processor. Here's an example of what the code will be. Includes standard input, standard output. And it's got while loop, the infinite loop there. Actually, before in the Python it was while true, which is also the infinite loop. So this is the infinite loop while 1, which is the classic way to do it. And same sort of thing, accumulated error. That's just the integration. That's storing the last value of the error, calculating the PID output, and then applying the control. And again, it's not. Of course, it's not using an interrupt. It's just waiting. It's using a delay. Let's see if it can put it in. That's not the sort of our Arduino method. That's the standard C one. See if it can do the same thing in Arduino. So let's say something like using Arduino. It's not really operating system, is it? Well, let's say just saying the Arduino method of coding. Code show me code for the PID controller using C. Let's see what it does. And it's gone straight in and did it. And there we go, that's the Arduino setup and the void loop. That's the infinite loop using the Arduino method. And again, it's very similar code to before. It's a real-time loop there, void loop. And this is set up what you're using. And I notice that it's using the serial communication here, 9600 baud. I'm not sure. It doesn't seem to. I'm not really sure what that's doing, because you're not actually using that in any way. But nevertheless, it's got the basis for everything. It's picked some default values for proportional, integral, and derivative terms. Let's see. Let's take something far more complicated and see if it can do it. Now, this was something I was thinking on lines myself to do as a research project, and maybe it's already done it. Let's say we can ask it in words to tell me the transfer, or let's say the FIR transfer function, or Z transfer function of an FIR filter with the following parameters. I'm just going to say spelling mistake. I'm just going to say passband, you can say 1 kilohertz. Stop band, you can say 10 kilohertz. It should be, I'll put a capital there, I don't think it'll make any difference. Stop band attenuation, let's say 40, say it's 40 dB. I suppose I should say passband ripple 3 dB. These are defined as positive, even though attenuation is it's defined as a positive dB, but it's negative in terms of gain. It's minus 40 dB down gain, but it's 40 dB of positive attenuation. And ripple 3 dB, that's a standard kind of ripple. I'm not defining the order of the filter because it should be able to work it out based on these parameters. Let's see what it does. I'd be surprised if it actually gives me the filter transfer function. Of course, I could do this on MATLAB anyway, but I wouldn't be able to ask the question in English. So that's the Z transfer function of an FIR filter to nth order. And it just says use one of the many available techniques. Oh, it's got an example here. Oh no, that's just the example of a transfer function. So it's a bit vague, so it obviously hasn't quite got to that level that I know of, unless I can find another way of asking the question. I wonder if it does analog filters. Let's try something like design. Oh, maybe I don't suppose it'll be able to show me the transfer function of let's see, oh, the second order Butterworth filter. So the capital with it's already second order with passband frequency, say 10 kilohertz, and stop band attenuation of, just to make it easy, 20 dB. So it's 20 dB per decade. So it should go down 20 dB by 100 kilohertz. I suppose I could mention the passband ripple, but I'll just leave that. It should default it to 3 dB. Let's see. So it's that's well, you see, this second order Butterworth filter, that's really the default Butterworth polynomial rather than this is sort of normalized one. Convert the passband frequency to radians per second. Okay. Calculate the natural frequency. Look at the values of D and omega n into the transfer function. It even gives me a how about that? Look, using that example, but that's I think is that actually done a transformation. What you have to do is a low pass to low pass transformation. I think it is doing it. Stop band attenuation and damping coefficient would be that. I think that is, though it's got a silly DC gain, it's got a gain of 1/5130, but nevertheless it's given us a good starting point anyway. Again, not quite there, but you can imagine if you took this to the next level, you could say design me a third order Butterworth filter with the following parameters, draw me the circuit diagram, manufacture it even, or something like that, you know, go and draw the printed circuit board. So I mean, this is just the start of something quite incredible. So if you want to have a go at it, it's ChatGPT, and good luck, and maybe you'll come up with something better than I've done here. Thank you.